Welcome to section 2.4, where we're going to learn about some new ratios called sine and cosine. And to do that, I want us to look at this diagram here. Notice that this is a diagram that contains what I call nested triangles, one inside another. Here is one. Here's another one. See how they're nested inside? One inside the other. And then finally this one over here. They are all right triangles, and all of them have a common ratio, common angle of angle A. So that one is common amongst all the triangles. Okay? I'd like you to fill out this chart. Okay, so looking at triangle A, I'll do this one with us together. What is the hypotenuse? In this case, the number is 5. What is the length of the side opposite of angle A? That would be 3. And the side adjacent of angle A, that would be 4. Now, once you've done that, can you calculate these ratios? What's the side opposite of A divided by the hypotenuse? Well, I think that's the ratio 3 over 5. Do you agree? Side opposite of A, 3, hypotenuse 5. What about the other one, side adjacent? Well, that would be 4 over 5. Good. So now I'd like us to do the exact same thing with this triangle ADE. The hypotenuse in this case, no longer 5, it's 5 plus 5, which is 10. The side opposite in this case is, you got it, 6. The side adjacent, not 4, but 4 plus 4, that's 8. Doing these ratios, I get 6 over 10. And this one, of course, is 8 over 10. Now notice 6 over 10 simplifies to 3 over 5. And 8 over 10 simplifies to 4 over 5. Interesting. Well, I want you to do the other ones, okay? Do AFG, and then do AHI. Then come back and double check your completed table with mine. And then let's see if we can answer those questions below. Okay? Press pause now. I guess you're back because you want the answers. So here we go. 15, 9, 12, 9 over 15, which happens to be 3 over 5. And 12 over 15, which happens to be 4 over 5. And then finally the last one, 20, 12, and 16. 12 over 20, which happens to be 3 over 5. 16 over 20, which happens to be 4 over 5. Now for each set of these triangles, how do these ratios compare? Well, they seem to be the same, right? This group, they're all 3/5. This group, they're all 4/5. Same. So what do you think the value of each ratio depends on? Yes, it's that target angle again. We've done stuff like this before when we talked about the tangent ratio, so let's generalize this to a general triangle with theta, the side opposite, the hypotenuse, and the adjacent. The sine ratio, so that's the one in the first column here. That would be the length of the opposite side divided by the length of the hypotenuse. So now we're looking at the opposite side divided by hypotenuse. The ratio is all the same regardless of the angle, or because of the angle. Then we have cosine, and that's this last column here. That's where we're going to take now the length of the adjacent side and divide that by the length of the hypotenuse. So the short form here, once again, sine theta is the opposite divided by the hypotenuse, whereas cosine theta is equivalent to the adjacent divided by the hypotenuse. Alright? Okay, knowing this, let's move on and visualize what I mean. So if I gave you this ratio here, sine of A equals to 0.5. Remember, sine, once again, is the connecting ratio of the opposite side divided by the hypotenuse. So that means if this ratio is half, then in any similar right triangle, the length of the side opposite angle A, that of course would be this one here, this length, is 0.5 times the length of its hypotenuse. It's half of this length. So for example, if this was 2, this would be 1. If this was 20, this would be 10. If this was 200, it would be 100. If you're looking at this ratio of 0.5. Okay? Now, if cosine of angle B was 0.8, then in any similar triangle, the length of the side, not opposite, but adjacent this time, angle B, which would be this side here, is, in this case, 0.8 times the length of its hypotenuse. So, of course, if the hypotenuse was 10, then this would be 8. If this was 100, this would be 80. That's 0.8 times. Okay? And that's what these ratios mean. So note, though, as angle A from the top goes from 0 to 90, so think about angle A being 0, like a really flat triangle, to angle 90 degrees, which is a really steep triangle. Notice that the ratio of sine then, right, which is the comparison of the opposite to the hypotenuse, that ratio is really small, and then this ratio here is pretty big. How big? Well, it's almost like 1. So I would say it goes from small to big. Really small starts at like 0, like when it's flat, and big means the ratio or that opposite side is pretty much equal to the hypotenuse, like 1. And vice versa, for angle B going from 0 to 90, the cosine ratio goes from, I hope you got this right, big to small. Really, the largest number here would be 1, because the ratio of the adjacent divided by the hypotenuse can't be bigger than 1. Remember, the hypotenuse is always the biggest side, and small is like almost like 0. Okay? Alright, if you get this, I'm really proud of you. Now, I'd like to see if you can apply it. So in example number 1 here, I've given you a triangle with all 3 lengths shown. Can you actually calculate the following things? Sine A, cosine A, sine C, cosine C. Well, if we're looking at sine A is my target angle. I always like to label the side. So here's my opposite, here's my adjacent, here's my hypotenuse. So therefore the ratio for sine A is defined as opposite over hypotenuse. That'd be 7 over 25. Cosine of A, yes, that's adjacent over hypotenuse, so that'd be 24 over 25. That's it, we're done. Now for sine C, I have to erase this because C is this angle, and notice that, the opposite side now is 24 because it's across from C. The adjacent side is actually the number 7, and the hypotenuse is still the longest side, is 25. So sine of C then in this case actually equals to the ratio 24 over 25. And cosine of C is the adjacent, so that's actually 7 over 25. So it matters which angle is the target angle you're looking at. So please be aware that the opposite and adjacent sides change depending on what target angle you are using. Okay? And so now, using the same triangles from above, can you calculate the measure of the following angles? So if I want angle A, I can use any of these ratios here. I'm just going to use the sine one for fun. So sine A equals to 7 over 25. Just like how we solved for the angle with tangent. In order to get rid of the sine ratio, we have to do the inverse sine feature on the calculator. So inverse sine here, second sine of 7 over 25. And that gives us the angle about 16.3 degrees. Okay, do the same thing for angle C. This time I'm going to use the cosine one just to have a little bit of variety. Cosine C is 7 over 25. So angle C once again is the inverse cos, or cos negative 1, of 7 over 25. I'm going to use my calculator again. Second cos 7 over 25 and 73.7 degrees. Okay? How are you feeling right now? I hope you're feeling okay about this. Because now I'd like you to try number 3. This time you have to figure out the unknown angle. And you have to decide which ratio to use. Well, here's my target angle. I better label the sides. This side must be the adjacent because it's next to the angle. And here's my right angle, so the 26 must be my hypotenuse. If I have the adjacent and the hypotenuse, which trig ratio should I be using? That's right, cosine. So cosine of angle theta is 19 over 26. And to solve for theta, once again, we take the inverse cosine. And on the calculator, inverse cosine, 1926. Voila, 43 degrees. Okay. I'm going to let you try example B now on your own. So press pause, work on it, then come back and check the answer. Hopefully you found that this is the opposite side. Hopefully you can see this is the hypotenuse. There's your right angle. Sine is your friend here. Let's go ahead and then do this ratio, the inverse sine of 12 over 13. Oops, that's not what I want. I want that. Oops, calculator, hello. Second function, sine, to get the sine negative 1, 12 over 13, 67.4 degrees. Okay? Happy? Good. Let's do some competency questions this time, okay? So I'll let you read it yourself, but I always like to draw a picture. And so once you've read it, draw a picture and double check your answer with me. A ladder 7.8 meters long, leans against the wall. Here's my ladder. 7.8. The base is 2.4 meters away from the wall. What is the angle of inclination? Remember, that's the angle measured from the horizontal going upwards. There you go. Hopefully then you can see this is the right angle. I hope that you can label the sides. Hypotenuse, adjacent. Which ratio should I be using? You got it. Cosine. Don't be afraid of decimals. The calculator is your friend in this unit. Cosine 2.4 divided by 7.8. Close the bracket. 72 degrees. That's pretty steep. But the right answer. Okay. Alright, turn the page. One last one. A cylindrical silo. I don't know if you even know what that is, but think of it as like a big cylinder that's filled with grain or something, okay? It's 40 feet high. That's pretty high. It has a radius of 5 feet, okay? Now the top of the silo can be reached by a spiral staircase that circles the silo 2 times. So imagine the staircase running around like this, right? And then encircling 2 times to get to the top. I guess I didn't draw this very well, but hopefully you can see the idea, right? And so the question is, what is the angle of inclination? So I knew I drew it kind of curvy, but hopefully you can see that there should be an angle of inclination right about here, okay? Now, if you're having a tough time visualizing this, I'd ask you to get a can of soup right now, okay? Seriously, get a can of soup or some canned good And I want you to like think of the label of the can as like the outer wall of the silo, and that your staircase is going along this outer wall. Okay. Now, if I were to unravel this outer wall, okay, hopefully you'll see that this actually becomes a nice rectangular piece of paper, where this is still the height of 40. But your staircase looks like this, starting here, going about halfway, and this point here is equivalent to actually this space right here. If you were to fold it around, then these two dots actually touch each other. So then the next staircase goes like this all the way to the top. Now the question I have for you is, what is the length of this base here? Because if I find that, I should be able to find the angle of inclination. So that's this right there. So the question is, what is the length of the highlighted piece in yellow? Well, that highlighted piece in yellow is equivalent to this circular perimeter. And that circular perimeter is called the circumference. That's right. And so what is the formula for the circumference? 2 pi times the radius. In this case, that's 5. So 2 times 5 is 10, or 10 pi. Pi is 3.14, so you could use 31.4. All right? So now you know this is 31.4. So how do I find the angle? If you're thinking, I have here the 31.4. That's awesome. Ooh, I need another side. Do I have the hypotenuse? Don't think so. Do I have the height? Yeah. Is it 40? Oh no, it's actually half of that, so that's 20, right. Okay, so I guess now I'm in business, because now I see a right angled triangle. What sides do I have? I have the opposite side, I have the adjacent side. Which ratio should I use? Is it sine? Wait, that's opposite of hypotenuse. Scratch that. Is it cosine? That's adjacent over hypotenuse. Oh, I need the hypotenuse. Scratch that. Oh, then I'm stuck. Well, I hope you remember the stuff you learned earlier in this chapter. Because opposite and adjacent, yeah, that's the tangent ratio. Tricked you. So, using the tangent ratio this time, you should be able to, find the angle. Yes, I know this is the sine and cosine chapter, but hey, we can throw in some review. You're going to be mixing them anyways later on in this unit, so why not do it now? Second function tangent, 20 divided by 31.4. Boom. 32.5 degrees. Okay. That's it for this topic. Here's your assignment. Go to it.